You're young, right?
Okay, hi everyone. So the plan is to talk a little bit more about linear approximation, and then we'll start talking about better kind of approximation, quadratic, and well, maybe this time or next time we'll start talking about Taylor approximation. Let me remind you what we did last time about linear approximation, what it is. So the situation was as follows. We had a function, some function, and we wanted to relate this function at some point s. So we wanted to find the value f of x for this function, but the problem was, well, for some reason the function was complicated, f of x was hard to compute. Instead, we could find out what is f of some nearby point, x naught. And what we did was as follows. We took this value and we drew a line. The best line that approximates our graph, the tangent line. And we said that, well, my graph is not exactly a line, but it's approximately a line. So f of x is approximately the same as the y value on this line. Well, what is this line? This line has equation y is equal to f of x naught plus f prime of x naught times x minus x naught. So this is this value. The value of y along this function, along this line. And our approximation was as follows. We wanted to say that f of x, this number on the graph, is not far away from the y value along the line. Is approximately equal to f of x naught plus the prime of x naught times x minus x naught for x which is close to x naught. And this was all there was to it. Just the graph of a function is close to the tangent line. And gave us an option to compute some things like, let's do an example, what is e to the power minus 0.1? Well, so this number is, well,
Close to 0.
just as it is written, it's hard to compute because it's what? It's 1 divided by 10th root of e. Not obvious what it is. But it is easy to compute e to some nearby power. What power?
0.
0, yes. So if we take our function to be e to the power x, we can easily compute it at a point x naught which is 0. Indeed, f of x naught, f of 0 is e to the power 0, which is 1. It is also quite easy to compute what is the derivative. F prime of x, well, for this function is derivative of e to x is e to x. So the derivative at the point x naught is e to the power 0, which is 1. And then we have the following approximation. For x which is close to 0, the approximation tells us e to the power x is approximately the value at 0, f of x naught, plus the value of derivative times x minus x naught, which is x minus 0. So it is 1 plus x. And finally, once we know how to approximate the graph of the function using the line, so this is the function, this is a line, we can approximate the actual values. E to the power minus 0.1 is approximately, well, 1 minus 0.1, which is 0.9. And now we do know that 1 over the 10th root of E is approximately 0.9. Not obvious at all, but well, correct. So yes, and also we learned last time how to know whether it's an overestimate or an underestimate. Does anyone remember how to do this? Whether this number is too large or too small?
Take the second derivative and see if it's concave up or down.
Yes. So if my function is concave, say down, like in this picture, then I know that the graph lies below the tangent line. And then any estimate using the tangent line will be overestimated. And vice versa, if it is concave up, then the graph will be above the tangent line, and the tangent line will give me an underestimate. So in this case, f double prime of x is, well,
Yeah.
to first explain what I'm doing. I'm deciding whether it is under or over estimate. So for this I compute the second derivative. At the point x0, it happens to be 1, it happens to be positive. So, well, my function is concave up. Well, maybe I can draw this chart. Function is concave up, so this must be an underestimate. So e to minus 0.1 is approximately 0.9 is an underestimate. So we know that e to minus 0.1 is approximately 0.9. Well, and I know it's a little bit larger. Not by much, but a little bit larger. Okay, so that's the general kind of outline how to do linear approximation for some simple functions like this. So maybe any questions about this reminder? Maybe it's worth pointing out that it's a good idea to actually, I mean, I chose this example because it's so easy to find the derivative, it's so simple to plug in the points. I want this example to show the outline, how to approach any kind of these questions. What, yeah? 0.9 was 1 plus x, and x was minus 0.
This is the part at the bottom.
Yeah. It's concave up because the second derivative is positive. So it's like in this picture, it's concave up, so it lies above the tangent line. I mean, if you want even more precise graph, it looks like this. X, e to the power x, like this. And what we did, we found the approximation at the point x equal to 0, happens to be equal, y is equal to x plus 1. So we found that the approximation is y is equal to x plus 1, and we try to plug in this point, minus 0.1. And we found out that the line gives me 0.9 here, and the actual value, well, I see it is a little bit larger. And I hope that it's not by much. So what I wanted to kind of emphasize here is that in a solution, all these steps, well, should appear. You should tell what is the function. You should tell what is the point that you are using to approximate this function. You should definitely find the value of the function at the point. Find the general expression for the derivative, not just at this point, but the general expression for the derivative. The reason you want to find kind of the general expression is, well, you can't really simultaneously compute the derivative and plug in the number. It doesn't work this way. Once you plug in the number, you stop having a function. You have just one number, and it doesn't have a derivative. Whether its derivative is equal to 0. You should find the derivative, then plug in the number into the derivative. Now you have this. You can write what is the linear approximation and when it is valid. When x is close to the value chosen, the linear approximation is such and such. And then you can answer the question. My number is close to such and such number. And maybe the only step from those ones which kind of it is maybe possible to skip but not really recommended to skip is this one, writing the general form of linear approximation. It is still a good idea to actually write the general form because then you can reuse it. You can reuse it to say that, say, e to the power 0.1 is approximately 1.1. You don't have to repeat the calculation. Okay, so next I want to do a different kind of question. Well, not much different. Still, I want to use linear approximation, but the question is as follows: what is sine of 1 degree? Approximate sine of 1 degree. Well, I can try to do the same thing. I can try to take my function sine of x, find the linear approximation, and I also see that, well, 1 degree is close to some value for which I can compute the sine. 0, yes. So 1 degree is really a tiny number. I mean, 1 degree is, well, kind of very, very small number. So, solution, try f of x, which is sine of x, x naught is equal to 0. Because I know that 1 degree is really a small number, really close to 0. Okay, so I have this. I will try to repeat the same. What is f of x naught? Well, it's sine of 0, which is 0. What is f prime of x? Well, it's derivative of sine, cosine. What is f prime at the point x naught? Well, it's cosine of 0, which is 1. So I get the following approximation for x which is close to 0. Sine of x is approximately 0 plus 1, the derivative times x minus 0, which is x. So for small x, sine of x is approximately x. Now a question. Does this mean that sine of 1 degree is 1 approximately? Well, of course no. I mean, it would be just ridiculous to think that sine of 1 degree is 1. Think about what is the sine of 1 degree. Remember how we thought about the sine. Sine of an angle is, well, take a circle of radius 1, measure the angle. Well, I should take 1 degree, which is quite a small angle. I mean, this looks more than 1 degree, but let's say that it's kind of 1 degree because otherwise it would be too small. And this distance is sine of 1 degree. If this is 1 degree. But 1 in this picture is this distance, the whole radius. Of course, sine of 1 degree is much, much smaller than this one. So it's not even nearly an approximation. Well, the second thought would be, well, I got an approximation, sine of x is approximately x. Here I have sine of not just 1, but sine of 1 degree. So maybe it's appropriate to say that sine of 1 degree is approximately 1 degree. Well, that's also kind of meaningless, because sine of something is the distance, or rather, well, ratio of two distances. It's not an angle. I should not be able to write such equality in approximate. Sine of an angle is a distance, something like this. No. Does it mean that we made some obvious mistake with they think that well, any graph should be approximated by its tangent line? Did we derive an incorrect approximation? Well, let's kind of put some substance inside of these formulas. What does it mean, sine of x? Well, so this approximation is about approximating graph of sine of x with a line. Let's try to think about the graph of sine of x. Well, first of all, I know it's some oscillating function. It looks like this. At 0, it is indeed 0. And then it oscillates. It oscillates between 1 and -1. At 0, it is equal to 0. Let's think about the x points here. At what point the sine is equal to 1? Where is the peak of sine? Pi by 2. Yes.
9 degrees.
Next one. Where does it cross the x line? Pi. Next one, the graph. 3 pi over 2. And finally, at 2 pi, it returns back. Okay, it's good. But then I look at this and I see that, well, I took this distance to be about 3.14. I did not take it to be about 180. 180 would look, well, kind of like this. No, I chose it to be 3.14. And it is about this graph for which, it is this graph about which this formula is valid. I can approximate this graph by its tangent line at the point 0. I see that in this picture, yes, it does look like sine of x is approximately equal to x, approximately equal to this line. But x here is not measured in degrees. Sine of 1 degree is not sine of 1. 1 is here, but 1 degree is much smaller. This is already 90 degrees. This is 180 degrees. 1 degree is 180, 1 over 100, I mean, it's 1/90th part of this interval. It's really tiny here. So for the formula the derivative of sine is cosine of x to be valid, x must be measured not in degrees, in radians. Let me recall what are radians. So radians are a funny way to measure kind of angles using distances. So if you have any angle and you happen to know that this length, so if this is a circle of radius 1 and this arc has length x, this angle measures x radians. That's what radians are. For instance, such an angle is pi radians. such an angle is pi by 2 radians. And then you know that what is 1 degree in radians? Well, 1 degree is 1 over 180 of this full open angle. This angle is 180 degrees. 1 degree is this angle divided by 180. So it's pi over 180 radians. Or in general, we have the following kind of conversion formula. If you want A degrees, it is pi over 180 times A radians. And now we can make sense of this formula. Sine of x being approximately equal to x when x is small. Well, in this case, it tells us that sine of 1 degree is the same as sine of pi over 180 radians. And we don't write radians because it's implied. When we say sine of some number, it's implied that this number is measured in radians. And this is approximately pi over 180. And now we do know what is sine of 1 degree. It's approximately pi over 180. If you want it in decimal, well, you can take a calculator or kind of approximate it. Pi is slightly bigger than 3. So pi over 180 is a little bit bigger than 1 over 60. So it's about 0.016. It's slightly bigger. Actually, well, if you take a calculator, you find that this is 0.01 7 4 5 3 and so on. And in fact, well, this approximation not only it is valid, it is actually very precise. We'll see a reason why it is so precise later, but actually if you try to find what is sine of 1 degree on your calculator, you'll find out that it's approximately, well, it is equal to 0.01745 and then some extra digits. So in fact, in these approximation, the first 6 digits are correct. It's not in general true that linear approximation is always that good, but in this case it is very good. I mean, the way to think about linear approximation is this. Okay, so I'll explain later why it is so good in this case and why in general it should be worse. But before I go there, maybe any questions about this? So once again, the lesson here is for formulas from calculus involving trigonometric functions to make sense, we must measure the angles in radians, not in degrees. So maybe to repeat this lesson without all these kind of digressions, let's do another example of similar kind. But now we'll do it a little bit faster. So find, well, approximate cosine of 60 degrees. Okay, so I want to approximate cosine of 62 degrees. First question is, I want to find a nearby value for which I can compute the cosine. 60, yes. So I do know what is cosine of 60 degrees. So we will use 62 degrees is about 60 degrees, and cosine of 60 degrees, well, we know what it is, it's 1/2. But even before we start actually writing down the derivatives, the approximation, and so on, let's convert everything to radians. Because we already see that the question is in degrees, and our formulas will be valid only once converted to radians. So to be on the safe side, let's convert everything to radians from the very beginning. So we'll use that 62 degrees is 60 degrees plus another 2 degrees. Now let's convert this to radians. 60 degrees is how many radians? 5 over 3 radians. So 60 degrees is 1/3 of this picture. And 2 degrees, well, maybe we'll use this formula. So it will be 5 over 180, which is 1 degree multiplied by 2. So it is 5 over 3 plus 5 over 90. And I actually do not want to convert it to just one fraction. I want to leave it as 5 over 3 plus something small, because this is what I will use for the approximation. And then I take x naught to be 5 by 3. I find out what is f of x naught. Sorry, I didn't tell what is f of x. F of x is cosine of x. So let me go all this over here. So the goal of x is 5 by 3 plus 5 over 90. F of x is cosine of x. X naught, I will choose it to be 5 over 3. F of x naught is cosine of 5 by 3, which we found out to be 1/2. Next, the derivative. Derivative of cosine is minus sine. So the derivative at the point x naught is minus sine of 5 by 3, which is, what is minus sine of 5 by 3? So it's minus the root of 3 by 2. So in general, you should remember that kind of for 30 degrees and for 60 degrees, you do have the values of sine and cosine. It's 1/2 and square root of 3 by 2. And to remember which one is which, it's maybe the most convenient to just imagine on the picture. So if you look at this picture, you have 90 degrees. If you divide it in 3 parts, you get 30 degrees and 60 degrees. And it's quite easy to see that this number is definitely smaller than this one. So if you remember that one of them must be 1/2, the other one is square root of 3 by 2, you know that this must be 1/2, and this must be square root of 3 by 2. And vice versa. This must be 1/2, and the larger one should be square root of 3 by 2. So I must admit that I mean, if you just ask me what is sine of 30 degrees, I wouldn't be able to tell you from my memory. I'll have to imagine a circle and imagine that, well, 30 degrees is not that large an angle, so it rises not that much. It must be either 1/2 or square root of 3 by 2. But, well, if I go even further, it will grow, so it must be the small, so it must be 1/2. So I can only remember it this way, otherwise I get confused. But anyway, so we find what is f prime of x naught. Next we find what is the linear approximation. for x which is close to pi by 3, we have that cosine of x is approximately cosine of pi by 3, which is 1/2, plus the derivative times x minus pi by 3. So it's 1/2 minus square root of 3 by 2 times x minus pi by 3. And only now we can find the actual approximation. Cosine of pi by 3 plus pi over 90, the one which we are interested in, is approximately 1/2 minus square root of 3 by 2 times the difference, which is pi over 90. So once again, because of the square roots of 3 and pi, it may be not the most convenient number to approximate in decimal without a calculator. I mean, so first of all, it is about 0.5. It is smaller than 0.5. By how much? Well, square root of 3 is 1.7, pi is 3, so the product is about 5, and 5 over 180, about 5 over 200, so it's about 1 over 40. I would say 0.025, something like this. So it's not that hard to actually compute what it is. So I would say it's kind of 0.5475. Let me check what it happens to be. Okay, so it's actually better. Well, if you take the actual calculator, you'll find that it's 0.4697. And in this approximation, well, this approximation is more typical than the previous one. Here you actually have only the first 3 digits correct, and the next one is off by 2. And that's quite a typical situation. So here you have cosine of 62 degrees is approximately 0.4697, and these 3 digits are correct. So I would say that it's quite typical of linear approximation to have, well, here you have a deviation from 60 degrees of 3%, 2 degrees out of 60 degrees is about 3%, and here you have, well, an error out of 469. So this is about 0.2%, so it's still quite small compared to the deviation here. But well, it's not like 6 digits like we have cosine. So that's much more typical. And also, like usual, we can know a priori whether it's an overestimate or underestimate. So if you want to know whether it's an over or underestimate, just compute the second derivative. F double prime of x is, well, derivative of minus sine is minus cosine of x. So second derivative at the point x naught is minus cosine of pi by 3. So it's minus 1/2. It's negative. So sine of 62 degrees being approximately 0.4697 is, well, my function is concave down. So the actual tangent line lies above it. So it produces an overestimate. So maybe questions now. Yeah. Well, first of all, I did it incorrectly. So I thought about, well, square root of 3 is about 1.7, pi is about 3, the product is about 5, the denominator is about, well, is 180. 180 is about 200, 5 over 200 is 1 over 40, 1 over 40 is 0.0. So, but you see, it didn't produce the actual numbers. I mean, I wanted to do a crude estimate of what it is, but it was a little bit too. I mean, probably the largest mistake was in this part. 180 is part of it. Other questions? So once again, the lesson here is, if you want to approximate some trigonometric function and the input is given in degrees, you must convert to radians to use this linear approximation. Because all our calculus formulas, basically we have just two formulas from calculus involving the derivatives of trigonometric functions, derivative of sine and derivative of cosine, but they are only valid when the argument is measured in radians. If argument were measured in degrees, we would have completely different formulas. Okay, so this was the last question on linear approximations. So maybe any questions in general about linear approximation before we go to a better one. Okay, so let's discuss a better approximation called quadratic approximation. So before we actually discuss what is the quadratic approximation, we want to discuss some motivation, some ideas behind it. So we still want to do the same task. Compute what is value of a function at a point if we know its value, the value of derivatives at nearby point. For a linear function, we use the following fact, that the graph of a function looks approximately like a line. And, well, it worked. For quadratic approximation, we'll use a different idea. We'll try to approximate a function, a graph of a function, not using a line, but rather using a parabola. Well, why do we think that it will be better than just a line? Well, because there are so many parabolas. I mean, if you take a parabola and make it kind of very, very flat, in the limit of this procedure, you will get a line. So in particular, lines are kind of degenerate cases of parabolas. But now we will allow to take these lines and bend them into parabolas and make them better approximations to our graph. So that would be the idea. So I'll start not with giving a formula, but rather with giving an idea of what we are trying to do. So idea, try to approximate f of x using not a linear polynomial, not a polynomial which describes a line, but rather a quadratic polynomial, something that describes a parabola. So quadratic polynomial looks like this. It has one coefficient plus another coefficient times something with x plus another coefficient with something with x squared. This describes a parabola. Well, I want this to be varied for x which is near the point x naught, to which I can compute the function. And the next part, well, I'm free here to choose three constants, C0, C1, and C2. They are completely up to me. And I want to choose among all possible parabolas. So here I have written lots and lots of parabolas. For any triple of coefficients, I get a parabola. I want to choose among all of those the parabola which approximates my function the best. Well, let me call this quadratic polynomial by p of x. I just give it a name. It's a polynomial of x of degree 2, and it looks like this. So how to determine for what coefficients this polynomial will be a good enough approximation of my graph? For what coefficients this graph will look like the parabola with such coefficients? Well, I have several things that I want, that I might want. At the point x naught, I want my parabola to pass through the point x naught, comma f of x naught. So like with linear approximation, in linear approximation I wanted the line to be passing through the actual point x naught, comma f of x naught. Same with parabola. I want the value of my polynomial, the point of the parabola, to be the same as the value of my function, the same as the point on the graph. I want the parabola to pass through the point. Next, I want the parabola in the graph to have the same tangent line. I want this parabola approximation to be at least as good as my linear approximation. So I want it at least to behave, well, to have the same tangent line. Once again, it's the same thing that I required for the linear approximation. In linear approximation, I was trying to choose among all possible lines, the line which fits my graph the best. Well, I chose the one which passes through the point on the graph, and also has the same slope as the graph at this point. Well, what does it mean? I want the slope of the tangent line of my parabola to be the same as the slope of the tangent line to the graph. Well, I might want quite a lot of things, but I'm not always free to actually get those things. In this case, let's think about how many things I kind of am allowed to want. Here I have three parameters, three coefficients, which I am allowed to change. I've written down two equations that I want to be satisfied. So to nail down the exact parameters which will be the best, I am allowed to want one extra thing, one additional equation. Well, I choose the following. I want my parabola to have exactly the same concavity at this point. So the line, the linear approximation, I wasn't allowed to bend this line. But now I am allowed. I can take this line and bend it into a parabola. A parabola has some concavity. And this is expressed by the value of the second derivative of the point x naught. Well, what I want is for the second derivative, for this how concave my parabola is, to be exactly like the second derivative of the graph, f double prime of x naught. So I require three things. My parabola passes through the point on the graph. It has the same tangent as the graph, and it has the same concavity as the graph. And now I impose three equations on kind of three unknowns. So I should be able to find out what are these unknowns. And indeed, let's rewrite these equations. What is the value of the polynomial? So first of all, if p of x is this polynomial, the derivative is c1 plus 2c2 x minus x naught. The second derivative is 2 times c2. And then I know that at the point x naught, if I plug in, instead of x, I plug in x naught. This part will vanish, this part will vanish, I'll get just c naught. And this I want to be the same as f of x naught. Next, the derivative at the point x naught, I plug in x naught instead of x, this becomes 0, so I get just c1. And I want this to be equal to the derivative of f. And finally, the second derivative at the point x naught is equal to 2 times c2, and I want this to be equal to the second derivative at the point x naught. So these conditions that my parabola goes through the point, has the same tangent and the same concavity, tell me what are the coefficients. What is c0, what is c1, what is c2. So all this was a discussion of the idea, how to choose among all possible parabolas in the plane, the one which in some sense fits my graph the best. And now I'll write down the final answer. What is the quadratic approximation? Well, it looks like this. F of x is approximately f of x naught, that's this number, plus the second number, f prime of x naught, times x minus x naught, and plus this third number, c2, which is f double prime at x naught over 2, times x minus x naught squared. So by making some arguments about, well, what I want to require from my parabola, I decided that this parabola would fit my graph the best. Because C2 is f double prime of x naught over 2. So this is C2 times x minus x naught squared, and C2 is f double prime of x naught divided by 2. So I decided that this parabola actually fits my graph the best. It passes through the point, it has the same tangent line, it has the same concavity. Well, I mean, I tried to argue as convincingly as I could that this is the best parabola, but maybe the examples, I mean, let's actually try to apply this to some calculations. If I do get something which is better than linear approximation, then probably I was right. If I don't, well, then it doesn't work. So let me start with an example that we already once considered. Let's compute what is the cubic root of 1001. So example, find linear and quadratic approximations 1001. Okay, so eventually we want to use this formula. Well, for this I first have to choose some number such that the cubic root of this number is easy to compute and this number is not far from 1001. What would be such a number? 1000, yes. Cubic root of 1000 is 10. So I will choose my function to be cubic root of x. I will choose x naught to be 1000. And then I'll compute all the derivatives. F prime of x is 1/3 x to minus 2/3. So f prime at the point x naught is 1/3 times 1000 to minus 2/3. So it's 1/3 times 1000 to power 1/3 is 10 and raised to minus 2. So it's 1/300. Next, the second derivative, f prime of x, f double prime of x. The derivative of the first derivative is minus 2/9 x to power minus 5/3. F double prime of x naught at the point is minus 2/9 times 1000 minus 5/3. So it's minus 2/9 times 10 to minus 6. So it's minus 2/9 times 1/, the derivative is 1/10 to the power 5. Just because I'm lazy to write zeros. And now I can write quite easily what are the linear approximations and the quadratic approximation. So let me start with linear. Cubic root of x is approximately equal to f of x naught, which is 10, plus the derivative 1/300 times x minus x naught, so x minus 1000, and that's it for linear approximation. Let me write down what is the quadratic approximation. Well, I'll use this formula. So cubic root of x, my function, is approximately, and it starts very similar. F of x naught, which is 10, plus the derivative 1/300 times x minus 1000, plus and then I have this extra term, second derivative divided by 2. So second derivative here is minus 2/9 times 1/10 to the power 5 divided by 2. So second derivative divided by 2 times x minus 1000 squared. And both approximations work well for x which is close to 1000. So for now I still didn't answer the question, what is the cubic root of 1001? But at least I know what the linear approximation, what the quadratic approximation tell me. The linear one tells me use this approximation, quadratic one tells me use this approximation. And we see that the quadratic approximation seems to want to correct the linear one. It wants to take the linear one and correct it, add some other extra term. Let's see whether it's successful. So, once again, linear approximation tells that cubic root of 1001 is approximately 10 plus 1 over 200 times difference between this and 1000 is 1. 1 over 300, 1/3 is 0.333. 1 over 300 is 0.00333. So it's 10.00333 and so on. Okay. Let's try the quadratic one. Once again, it starts in exactly the same manner. It's 10 plus 1 over 300 times 1. And then it has this correction term. Minus 1 over 9 multiplied by 10 to the power 5 and times 1. So I canceled out the 2 from here. And I have minus 1 over 9 times 10 to the power 5 and times, well, let me write this once there. So I just plug in x equal to 1001 into this formula. Well, so what do I get? It's 10 plus 0.00333 and so on, minus, well, 1 over 9 is 0.11111. So this number is 0.50, and so on. So if I combine all of those, I get that this is 10.00333. So I don't change anything for 5 places, and then I replace the next ones by 2, 2, 2, 2, 2, and so on. Well, I wrote a huge number of digits here as if I'm sure about their correctness. Well, let's check. So does anyone have a calculator?
Yes, 10.0033322. That's all the calculator gives me.
Okay. So the calculator tells us that our quadratic approximation is correct to 8 digits. And the calculator is not sure about the next one. We're also not sure about the next one, and actually it is wrong. But it's not, well, very wrong. It's wrong by a little bit. So this quadratic approximation is in fact, well, in this case just fantastic. The linear approximation was good. I mean, it verified that it's correct up to here, 6 digits. But the quadratic approximation is simply fantastic, as good as a calculator. So, yes, we did improve on the linear approximation. In this situation, the quadratic approximation is just much, much, much better. Well, okay, so maybe first questions about this. So, in general, it is true that quadratic approximation is always, well, almost always better than the linear one. The only kind of caveat is the point should be actually close to the, I mean, this 1001 and 1000 were actually very close. They were within, well, one part of 1000, within 0.1% of each other. So in this situation, first of all, both approximations will be good, and the quadratic one will be much better. If the points are far away, well, some strange things might happen. Sometimes both of them will be bad, sometimes one of them will be better, but usually the quadratic one will be the one which is better. Yeah.
Expand again at the very beginning. Why do we call the original function and the first and second derivative?
Oh, I see. So what we try to achieve is, the question was to explain once again why we try to make the derivative of, well, this quadratic approximation, such a quadratic approximation, to be the same as derivative of the function. So the reason I want you to do the following. So in approximation, I try to approximate the graph of a function by some geometrical shape. One geometrical shape is, say, a horizontal line. If I know that here is my point x0, the horizontal line, the best one to approximate the graph, the best horizontal line that approximates my graph is such one. I can't choose a better one. It actually passes to the point x0 and is the best one. If I make it farther away, well, it will not pass to this one. Well, if I allow myself not just horizontal line, but any kind of line, well, I have two things. First of all, I still want my line to pass through this point. Just because I want at this point my approximation to be precise. But then I'm free to choose among the lines which pass through this point, the one which approximates my graph the best. So I'll choose the line which is tangent to this graph. Which means this line will have the same slope as the graph, right? Okay. Next thing, I'll try to approximate my graph not using even a line, but using a parabola. I will allow to take my line and bend it. Well, how much should I bend it? Well, I still want whatever shape I get to pass through this point. So that would be the condition that f of x0 is the same as whatever my shape is at the point x0. I still want the condition that whatever shape I will get should have the same tangent line. So I still want both of them to be, well, increasing at the same rate, to have the same tangent line. That condition is, slope of my function at this point is the same as slope of whatever shape I'm using. Well, it turned out that these two conditions are still not enough to determine the shape. And I'm still free to choose one more condition. The condition that I chose was like this. Let me change it, kind of bend it so much that the concavity at this point, how much, to what extent it is concave. So different concavities look like this. Function which is not really concave, function which is more concave, even more concave, and very much concave. That's about how large is the second derivative. I choose them to be also the same. So I want the shape to have the same concavity as the function, as the graph. And this translates to such a condition. Okay? Okay, so we had this. Last time we also have seen an example where the point where we tried to find the function was not that close to the point where we could evaluate the function. So another example would be, what would be the square root of 13? Well, last time we argued that square root of 13 is hard to compute. What was easy to compute is either square root of 16 or square root of 9. Well, which one we choose as our x naught, 9 or 16?
Either is fine. Either is fine.
Well, I would argue that between these two choices, the 16 is better. Why is it better?
Because it's closer.
Yes, first of all, it is closer, and also, so the difference between 13 and 16 is just 3, and between 13 and 9 is 4. But also it's closer in relative terms. So if you go from 13 to 9, you have to make a jump of 4 out of 13, which is,
Two.
okay, maybe it's,
Just trying to think of this one.
it's rather the opposite way. To go from 9 to 13, you have to make a jump of 4 out of 9, which is kind of almost 50%. And to go from 16 back to 13, you have to make a jump of 3 out of 16, which is only 25%, well, even smaller. So it is better in fact to choose 16. So let me choose f of x to be square root of x, and x naught to be 16. Then I'll compute what is the derivative, what is the second derivative. So derivative will be 1/2 x to minus 1/2. So f prime at the point x naught is 1/2 times 16 to the power minus 1/2, which is 1/8. Then I'll compute what is f double prime of x, which is 1 minus 1/4 times x to minus 3/2. F prime of x naught, f double prime of x naught is minus 1/4 times 16 to minus 3/2. So it's minus 1/4 times 1/4 to the power 3. So it's minus 1/4 times 1/64. So it's minus 1/256. So we found, well, the first, second derivative and the value of the function. We can use the quadratic approximation. So we can use the square root of x is approximately the value of the function at the point 16, which is 4, plus the derivative times x minus 16, and plus the second derivative divided by 2 and multiplied by x minus 16 squared. Just a small comment. I don't know how, but do remember to divide by 2 here. It's easy to forget after all these computations, but it is really important. Otherwise, you get an approximation which is really not that much better than preliminary. Okay, so we have this approximation. It works for x which is close to 16, and we hope that our point 13 is close enough for this approximation to be valid. Well, let's check. Square root of 13, according to this, is approximately 4 plus 1/8 times 13 minus 6, which is minus 3, minus 1/2 times 256, and multiplied by minus 3 squared.
Oh, your x.
So we get the following answer. Square root of 13 is approximately 4 minus 3/8 minus 9/512. Okay, let's convert it to decimal. So first of again, if you look at this, it is exactly what used to be a linear approximation plus an extra correction. Let's think about what it is. It's, well, let me write it in this way. It's 4 minus 3 over 8 minus 18 over 1024. And now I'll use it. 1024 is about 1000. So that's approximately 4 minus 0.375 and minus 0.0018. So it is about 4.6 25 minus 18, 0.7. So, I mean, I went from the actual quadratic approximation, which is this one, that's the actual answer. I wanted to convert it to decimal and not use a calculator, so I did some trick, and well, here's the answer that I find.
It should be 3, right?
Yeah.
3.6.
So 18 over 1000, so I should
You need to subtract it.
2,
Never mind.
3, so 0.018. But I did write it correctly.
No, it's 3, isn't it? 4 minus 0.3.
So 4 minus this is 4, oh, of course. I should actually read it. Something was wrong here, now it's 3.607. Okay, so I hope that this is now correct, or at least approximately correct. Let me just say, well, recommend that a linear approximation to this would be just these first two terms. It would be square root of 13 is approximately 4 minus 3 over 8, which is 3.67625. And so, does anyone have a calculator to actually verify what it is?
Oh, no, yeah.
What is square root of 13?
3.60555.
So square root of 13 is actually 3.6055. So, in fact, in this approximation, in the linear one, we got just 2 digits correctly. In the quadratic one, even with my imprecision and well, all the mistakes, we got at least 3 correctly, and also the next one is off by just kind of 2 or even 1.5. So this is pretty close. So even for a point which is quite far away from the actual nearby point, which is 16, well, we do get a quadratic approximation which is quite precise, first of all, and better than linear one. No, so basically the typical question would ask you, well, find the linear approximation, or find the quadratic approximation, or find the Taylor approximation, what we will do next time, not compare them. So the comparison here is just, well, to show that, yes, actually it is better than the previous. Sorry? Yes. Yes. Okay, so maybe I won't start a new topic now, I'll just advertise it. So next time, so we get this approximation using the quadratic polynomial. Well, the next idea is why stop at the quadratic polynomial? Let's introduce q vector.
No.
Degree 4
No,
there.
no,
Degree
stop.
5 there.
Stop it. No,
Well,
stop.
why stop here? Why stop at 5?
Stop.
Let's introduce anything Riemannian first. Yes, it will go. You can see next time.
Taylor polynomial. Stop.